So let's do a couple more related rate problems, or maybe just one more, but nonetheless, more related rate problems. So let me call this section pre-calc for related rates. So again, remember I mentioned in the last video that sometimes students aren't thrilled with this material or this section of these courses, and unfortunately, it's the fun aspect of them that sometimes people don't like, and why they're disliked is because you have to use a lot more than just calculus to do them. All the math you learned throughout your high school career, or maybe in your pre-calculus course, college algebra, what have you, whatever you've seen, whatever you've taken, whatever you'll eventually take, and you need to use a lot of these things together in order to solve related rates problems. So, for example, in the last problem, I just sort of put it up there, but we did need to know the formula for the volume of a sphere in terms of its radius in the last problem. Here, let me mention something that comes up quite a bit. Please know that I am not saying that this is the only technique you need to know, but something that comes up quite a bit in related rates problems is similar triangles. So let me come up with a problem for you. I'll mostly just say it verbally, but imagine we have someone who is walking away from a building. Maybe let's make him about this tall to make the picture better. And let's say that the building is 10 meters up the building. There is a light that shines down. And let's say this person is 2 meters tall. So we have light shining out. Okay, and of course that's going to make a shadow be cast. So the shadow is going to end around here. And we can ask the following. So suppose this person is walking at a speed of, what's a good speed that they could be walking? Let's say that this person's walking at a speed of 1 meter per second. And we can ask, okay, if the person's walking at a speed of 1 meter per second, how fast is the tip of the shadow moving? Okay? And you can sort of imagine something like this in your head. You've seen this in real life, you've walked away from a light, you know that the shadow, it's not going to go super duper fast, but it's going to move a little faster than the person. Think in your head about how shadows work. So let's figure out what it actually is going to be. So let's set up some variables. Well, let's say L1 is the distance between the person and the building. Now, why am I calling it L1 as opposed to D1 when it's a distance? Well, you can also talk about the length between a person and a building, and derivatives use this letter D. So I'm purposely trying to not refer to variables with the letter D. That's why I called this L. It's good to think about giving variables reasonable names, but you have to ask yourself when these names are indeed reasonable. So let's avoid D here. And we definitely care about how fast the person is moving. So we care about this variable L1 because that's basically what's given. If this person is walking at a speed of 1 meter per second, that is precisely saying that the rate of change in time of L1 is 1 meters per second. We're being asked about how fast the tip of the shadow is moving. So let's say L2 is the distance between the building and the tip of the shadow. So this one here, again, is our given. And how this problem works is that our desired is what dl2 by dt is. So this is what we're trying to solve for. Okay? So now, what do we have to do? Well, we can set up our sort of same equation as before, this same sort of standard related rates type equation, for the same reasons as before. And what we can say is, well, dl2 by dt is going to have to be dl2 by dl1 times dl1 by dt. So I did that fairly quickly. There's a couple of ways you can think about this. One way you can think about this is, indeed, you could work it all out exactly in the same way as I did in the previous example, but Don't think of these d something by d something else's as fractions. That'll get you into trouble, but unfortunately it is a sort of a good memory device, and indeed why this is going to be true is you can sort of imagine in your head why this product is equal to this symbol here is, in order to remember it, you could think of the dl1s as canceling. So everything that applied to the previous case applies here too, but I think the fastest way to sort of sink your teeth into these problems is to just write something like this down and go forward from there. So of course, what is this? Well, this is given, this is desired, so the meat of the problem is to figure out this term here. So how does this work? Well, what we're going to need to do is we're going to need to write out L2 as a function of L1, and then we're going to have to differentiate this function in L1. How do we do that? Well, how we do that is via similar triangles. So let's recall what similar triangles are. Suppose I have two triangles like this, and they are similar. What does similar mean? Similar means they have the exact same interior angles. So suppose we have this tiny triangle here with side lengths A, B, and C, and this other triangle, and it's the same shape, like if you sort of worked in Photoshop or Paint or some other photo manipulation program. You just sort of took this guy and you increased it in size without changing any of the angles. And let's say that its side lengths are D, E, and F. So what similar triangles says just says that the same factor that requires you to scale up A to D is the factor that requires you to scale up B to E. And one way to write that is that D over A is equal to E over B. Of course, this is also equal to F over C for the same reason. So how can we apply this to the case here? Well, note, these are two right triangles. This little triangle is similar to this big triangle, and the base length of this little triangle is going to be L2 minus L1. So what do similar triangles give us? It gives us that L2 over 10, the base length of the big triangle divided by the height of the big triangle is equal to L2 minus L1 over 2, the base length of the little triangle divided by the height of the little triangle. But now we can solve this. This turns into 2L2 is equal to 10L2 minus 10L1. All right, and this means that 8L2 is equal to 10L1. All I've done is I've brought over this 2L2 over to this side. I've brought the minus 10L1 over to the other side, and I suppose I switched the sides, but I don't think that's too terribly confusing. We get this equation here, notably that L2 is equal to 10 over 8, which is 5 over 4, L1. But of course now we can differentiate this function in L1. And this means that dL2 by dL1, well, this is just a degree 1 polynomial in L1, so this is just going to be 5/4. So now I'll do it over here because it's the only place I have some room. Putting everything in, we get that. So dL2 by dt, which we don't know and we want to know, is equal to, well, this thing is 1, which we know, and this thing we just computed is 5/4. So indeed, the shadow is going to be moving at a speed of 5 over 4 meters per second. And that's how this works. So again, we wrote down this sort of inaugural main equation that's always going to govern these types of related rates problems. And this equation, we worked it out so that it included both the given information and the desired information. This left us with this one quantity that we had to figure out ourselves, and these problems can go lots of different ways. In the previous case, you had to use knowledge about what the volume of a sphere was in terms of its radius. Sometimes, in a classroom setting, that would be given as part of the problem. I've definitely given that information on tests and not had people memorize that formula in the past. But here, you have to figure it out yourself, and the technique to figure it out was exactly this similar triangles idea. This here exactly was our fundamental use of similar triangles, which allowed us to relate L1 and L2. But once we had this equation, it was just a hop, skip, and a jump to getting this formula for L2 in terms of L1, this formula for dL2 by dL1, and that's the answer. So all sorts of techniques, all sorts of pre-calculus, high school type ideas can come up in problems like this. They can get very difficult, they can get a little hairy, but this basic structure that happens both in this example and in the example from the previous video are how they all work. Just be very careful picking your variables, noticing what's given, what's desired, how to work out the other bit of information, and if you do all of that, you'll be good.